All right, so we want to find the extreme values of the curve x squared plus y squared subject to lying on the constraint curve x plus 2y equals 6. So we're going to use LaGrange multipliers to do this. So we need to look at our gradient of our function f. And that is going to be the vector 2x, the partial with respect to x, 2y, which is the partial with respect to y. And then we're going to look at the gradient for the constraint. I'm just going to call that c. And that is going to be the partial with respect to x is 1, the partial with respect to y is 2. And we know that the relationship between these is that there's some number lambda, so that one is so that something like the gradient with respect to f is lambda times the gradient with respect to c. And you can put lambda on either side depending on which is most convenient, but we're going to get here that 2x is equal to 1 times lambda, and 2y is equal to 2 times lambda. And in other words, this is the same as y is equal to lambda, which tells us that 2x must be equal to y in that case. So then once we know that relationship between our x's and y's, we can plug into our constraint, and we get that x plus, since y is twice x, we get 2 times 2x equals 6. So that's x plus 4x equals 6. So 5x equals 6, and x is 6/5. And we know that y is twice as big as x, so y is then 12/5. And so, but the question asks what's the extreme values for the function. And so if we look at this, f of 6/5, 12/5 is going to be, say our curve was x squared plus y squared, so we're going to get 36 25ths plus 144 25ths, which is 100 and something, I don't know. 144 plus 6 is 180 over 25, which can be simplified down. If we divide that by 5, we get 36/5. And notice that as x and y get larger, x squared plus y squared gets much, much bigger than 36/5. So this is actually a minimum value. It won't get any smaller than that on that curve. And it has no maximum value on the line x plus 2y is equal to 6. All right, do the same thing here. So we're going to use LaGrange multipliers to find the extreme values of f of xy equals xy, subject to x squared plus y squared equals 10. So let's look at the gradient of f. That is going to be y x when we look at the partial derivatives, and the gradient of our constraint is going to be 2x 2y. So again, we know that the relationship between those two is that the gradient of f has to be some number lambda times the gradient of the constraint. So when we do that, we know that 2x is lambda times y, and similarly we know that 2y is lambda times x. And so that means that lambda is 2x over y, and lambda is also 2y over x, so that these two things must be equal to each other. 2x over y has to equal 2y over x. In other words, 2x squared equals 2y squared. So that gives us that x squared is y squared. And square rooting both sides, we get that the relationship between them is that x is plus or minus y. X is plus or minus y. So let's plug those into the constraint. So first I'm going to do x is positive y. So then our constraint becomes x squared plus x squared is equal to 10. 2x squared equals 10. So x squared is plus or minus, so square root of 5. And since y is equal to that, we're going to get square root of 5, square root of 5 as one possibility for an extreme, and negative square root of 5, negative square root of 5 as the other possibility. And let's evaluate the function at those. So f of root 5, since f is x times y, that's going to be 5. And f of negative root 5 is also going to be 5. And now let's look at when x is negative y. We're still going to get the same thing, right? We're still going to get that x squared plus x squared is 10 because we can replace y with negative x so that x is plus or minus the square root of 5. But now when we write our points, if we pick x to be positive square root of 5, then y is the opposite of that. And if we pick x to be the negative square root of y, then x is the opposite of that. So we're going to have opposite signs this time here, which means that when we multiply them together, we're going to get negative 5 this time. Which means that these 2 points here were giving us the maximum. The maximum value is 5 at these 2 locations. And then we have a minimum value of negative 5 at these other 2 points. All right, we're going to take this into 3 dimensions now. Same idea though. So we're going to look at the gradient of f. We have, it's going to be the vector 1, 1, 1. And then the gradient of our constraint is going to be the vector 2x, 2y, 2z. So that we know that 2x equals lambda, 2y equals lambda, and 2z equals lambda, so that x equals y equals z. Now we plug that into our constraint, giving us x squared plus x squared plus x squared, since all of them are equal, equals 16. So we get 3x squared equals 16. So x squared is 16 over 3, which means x is plus or minus 4 over the square root 3. And we know that x, y, and z are all equal to each other. So we get that f of positive 4 over root 3, 4 over root 3, 4 over root 3 is going to be those 3 added together. So we get 3 times 4 over root 3, which is 4 root 3. And if we choose them all to be negative, we get 3 times negative 4 over root 3, which is negative 4 root 3. All right, we're going to do one more. This time, I don't have this one typed up, but we're going to find the point on the plane so the plane we're given is 2x minus y plus z equals 3, and we want the point on that plane that is closest to the point 1, 2, negative 1. So in this case, the equation for our plane, this becomes our constraint, right? It constrains what points are possibilities in our answer. So the thing we're trying to minimize here, since we want closest, we're going to minimize the distance from the point to the plane, but the distance between this point and any other point out there is going to be, we'll actually minimize the distance squared. That is going to be x minus 1 squared plus y minus 2 squared plus z plus 1 squared from our three-dimensional distance formula. So the distance between the given point and any other point is this formula. Well, we're just going to minimize the square of the distance, which is the same thing as minimizing the distance, just slightly easier because we don't have to deal with square root. And we're subject to the constraint that the points that we can look at have to lie on our plane. So let's look at the gradient of our distance squared. And that is going to look like the vector 2 times x minus 1, 2 times y minus 2, 2 times z plus 1. And the gradient for our constraint is going to be the vector 2, negative 1, 1. All right, so we get that, then that 2 times x minus 1 is equal to 2 lambda, or in other words, x minus 1 is equal to lambda if we divide by 2. And then we get that 2 times y minus 2 is equal to negative lambda. And then we also get that 2 times z plus 1 is equal to lambda. So let's work with so this is going to give us that x is equal to lambda plus 1. This one here, we get y minus 2 is negative lambda over 2, so that y is equal to negative lambda over 2 plus 2. And then we get that z plus 1 is lambda over 2, so that z is equal to lambda over 2 minus 1. And now what we're going to do is we're going to plug those into our constraint. So we're going to rewrite our constraint in terms of lambda and solve for lambda. So we get 2 times lambda plus 1 minus negative lambda over 2 plus 2 plus lambda over 2 minus 1 is equal to 3. All right, so now we get 2 lambda plus 2 plus lambda over 2 minus 2 plus lambda over 2 minus 1 equals 3. So let's see, I have 3 lambdas because I have 2 lambdas here, and then I have a couple half lambdas, plus or minus 1 equals 3. So 3 lambda is equal to 4, and lambda equals 4/3. So now our point, we know that x, y, z looks like lambda plus 1, negative lambda over 2 plus 2, and lambda over 2 minus 1. So that becomes, the point we're looking for is 4/3 plus 1, so that's 7/3. Negative lambda over 2 is going to be negative 2/3 plus 2, so that's 4/3. And then lambda over 2 minus 1, so that's 2/3 minus 1, which is negative 1/3. So this point lies on our plane, and it is the closest one to the given point.